Part 2 is going to make up what I think is the bulk of most of my lectures tomorrow. And I think what I'm going to do is, after talking with Guy, is I'm going to do as much introductory stuff today as possible. So I'm going to proceed in this part 2 up until essentially the end of this segment here. And then in our last segment, I'll swap to part 3, OK? So that I can cover more introductory stuff early on. And that'll hopefully ground you guys a little bit better for what Guy's going to talk about. Unfortunately, he'll talk in a totally different context. So part 2, I'm going to start with an introduction to many-body theory. And that's because from talking with people, I think that actually will have some value. Now, when I say introduction, I'm not deriving many-body theory. This is another one of those subjects that can and should have a full course devoted to it. I'm just going to identify what the basic objects are, what their symbols are, what they mean in some cartoon-like manner, so that as we proceed through talking about physical problems that involve these many-body objects, you have an idea of what's going on. Okay? And for the experts who have already taken courses in many-body theory or work in many-body theory, this won't hurt you at all. Okay? So you just have to deal with it. So once we do that, when I come back, I'm going to start talking about the Hubbard model. And I'm going to introduce it from its basics. And I'm going to start talking about, because the theme of my lectures is supposed to be about phase transitions, I'm going to primarily try and focus on phase transitions. I'm going to talk about the first order phase transition in the Hubbard model, which is a metal insulator transition. Okay? Then I can talk about second order phase transitions. You have things like nail transitions in 3-dimensional problems. You have false nail transitions in 2-dimensional problems that are finite, so that it's not in the thermodynamic limit. And I'll talk a little bit later about superconductivity. Once I've talked a little bit about that, I'll talk about extensions of the Hubbard model. Okay? That means you'll see later adding non-local interactions, and how you still get metal insulator transitions, but those are somehow modified by inserting non-locality into the interaction. And you can also get charge ordering. Now, once I get through that content, I'm going to go further. I'm going to talk about generalized susceptibilities actually all of that's in my many-body intro. Generalized susceptibilities. I'll talk a little bit about magnetic pairing and density channels. I'll talk about introduce the Bethe-Salpeter equation. I'll talk about screen interactions, vertex functions, and Hedin's equations. And I'll give examples at the end of all of that stuff from superconductivity. Okay? In there somewhere, I'm also going to talk about solution methods. Since I've been a postdoc, I've mostly been doing numerical work. And so this involves a variety of numerical routines that allow us to attempt to solve the Hubbard model. And I'll actually talk a little bit about one of those, diagrammatic Monte Carlo, in a little bit when I jump on to part 3. Okay? And throughout here, you'll see I'll talk a lot about decoupling schemes. And I'll talk about Hubbard-Stratonovic transformations, which ties in very well with part 1. I'll also mention that, especially in extended Hubbard models, you have other decoupling schemes, but the role they play is sort of the same. Okay? You have problematic terms in a Hamiltonian, and if you come up with the correct transformation, you can somehow reduce the problem to local, more tractable problem. Okay? And then at the end, I'll talk about duality. And I do that because I've done a lot of work on a method called dual fermions, which Alexei is essentially the inventor of. All right. So I like to start with as general introduction as possible. So I just want to remind what it is that we're doing here. We are physicists with different backgrounds. And we know that there are 4 fundamental interactions in nature. And you go to Wikipedia, and you find this nice table. What we want to try and do is we want to understand how to solve a problem such as electrons in a solid that has 10 to the 23 particles. So that's referred to as the many-body problem. But for condensed matter physicists, we don't care about most of our forces. Okay? So this is a really boring diagram. So I don't know if you guys know the comic XKCD. This is the equivalent table, okay, that outlines our understanding of the forces of nature. There are 4 fundamental forces between particles. The first one is gravity, that obeys this inverse square law. The second one is electromagnetism, that obeys that inverse square law. The strong nuclear force, this is a very good representation of my understanding. It's strong. And the weak force is mumble, mumble, radioactive decay, mumble, mumble. And yeah, those are the 4 fundamental forces. Hooray. So I just want to emphasize that most of that we don't care about, right? We are actually acting on we're working on systems where all of the physics is controlled by electromagnetism, and we understand electromagnetism. OK? Hooray. Yeah. We understand it. OK? And there's an interesting quote that comes from Anderson from 1972 that gets regurgitated in all talks on strongly correlated systems. And the reason for it is that it was right after the observation of quarks in high energy physics. So suddenly high energy physics becomes a very interesting thing. And condensed matter physics is like, oh, it's already understood. You already understand electromagnetism, right? So in defense, you know, he gets his hackles up, you know, on a cat when it gets mad, the fur on the back of its neck stands up. And this idea that in a complex system, you know, there's fundamentally different behavior when you have 10 to 23 particles than when you have just a few particles. And this is where all of these phase transitions come from, is actually having thermodynamically large numbers of particles. So I don't know if he coined the phrase or others did, but this idea of searching for emergent behavior. And that's how you justify working in condensed matter physics, is that there's really cool emergent physics that comes out. So emergent properties are characteristics of a collection of objects or complex system that the individual members do not have. Okay? And it happens at all scales and all walks of science. Electrons in superconductors, for example, expel magnetic fields, and that results in levitation. And that's something that just a few electrons on their own certainly would not really do. Biological systems, nucleic acids combine to form DNA. You as a person are constructed of a series of organs. But if we took all your organs out and put them on the table, we would not say that that was you, right? We're not going to do that, unless we all get really sick, I guess. I hope there's no virus that causes us to invert that way. All right, so what we want to do is outline the tools and methods of many-body theory to help deal with problems when you have 10 to the 23 particles. So I added this slide because somewhere on our walk yesterday, there was a discussion with someone, I forget who, as to what is a strongly correlated electron system. Does anyone have a definition of strongly correlated electron systems? Any definition? Misha, you want to say something?
Well, maybe it's a quantum theory of fermions where perturbation theory-based methods are not applicable, maybe?
That's a good definition. Where perturbative methods are somehow not applicable. So that could be one option. An alternate definition might be any problem where density functional theory fails within its simple approximations. There are other definitions where low-order perturbation theory fails, or where infinite-order perturbation theory fails. That's also if you have some sort of non-perturbative problem. Or you could say, well, when mean field theory fails, I must be in a strongly correlated system. Okay? So I just want to identify that when someone walks up to you and says, hi, I'm James, I work on strongly correlated electron systems, that could mean just about anything. Okay? So here's my intro to many-body theory. Again, you should have a whole course on it. But I think I do it in like 10 slides. Okay? Which means you can't actually do anything with it, but you'll understand some of the symbols. So just a reminder, again, we're just concerned with Coulombic type interactions in our electronic system. And at least for me, the most fundamental object we can look at is a single particle Green's function. And you've probably encountered Green's functions in other contexts in physics. Green's functions are typically tools which let you solve some sort of differential equation, right? And you have a differential equation that has a right-hand side, and it has some potential term or a charge density, and you throw it out and you replace it with delta functions, and you solve the problem, you get your Green's function, and this gives you your tool to solve the more general problem that has a potential in terms of that function. Okay? This is exactly the same. It's just applied to a many-body context. So we work in what's called second quantized notation. How many of you are familiar with second quantized notation? Almost all of you. That's excellent. The idea of this notation is that we have an operator that acts, that has as its arguments 2 different points in space and 2 different points in time. Here's 0 and tau, which tau is some complex time typically. It can be a real time as well. And then we have 2 points in space, r and r prime. And we're going to take, on average, what happens when we create a particle. So we have the creation operator with the plus sign there. We're going to put a particle in our system at time 0, and we're going to allow it to propagate through the system. And at some later time tau, we're going to take it out of the system. And that system is some background that has 10 to the 23 particles. Okay? So this is referred to as a single particle correlation function. And if you repeat this process of putting the particle in and pulling it out, again and again to build a probability of being in a particular final state at a certain time, then this gives you all the information you need to understand the density of states of your system. Okay? You understand exactly how things propagate in your system. So my favorite textbook on many-body theory is an old one that is probably super out of print called Mattuck, because it has all of these cartoons. And have any of you? It's not out of print. Is it still being used? Good.
Which textbook put in the briefcase? Or right now?
Mattuck. M-A-T-T.
Who's the author?
That is the author. It is Mattuck's many-body theory.
That book is colloquially known as Feynman diagrams for idiots.
Yes, Feynman diagrams for dummies. It is an excellent starting point for understanding many-body theory. And in there, he has very fun, colorful pictures. And so, for example, right here, we have Dima, who's hiding in the back. And this is a picture that's called Propagation of a Drunken Man. And the idea is that at the start of the evening, he begins at a party. And as the evening progresses, he goes to a club and a bar and Alice's. And sometimes at the end of the night, sometimes he winds up at home. Sometimes he ends up at his friend's apartment. Sometimes he's sleeping in a ditch. Okay? And the idea is that if you just did this every weekend, you went out to the bar, and you tracked where you wound up at the end of the evening, you would build a probability distribution that represents where you end up sleeping after a night out. Okay? And if you don't actually care about which bars you went to, then maybe this helps you solve a problem, right? It lets you know if I'm, we're going to say this person, I'm picking on Dima. This is Dima, and I want to know where he is at the end of the night. I can guess with good certainty there's a 50% chance he wound up at home, and a 50% chance he wound up at a friend's apartment or some such thing. Okay? So this allows us to statistically solve a problem, and it's the same idea with electrons in a system. OK. So Feynman diagrams are a tool which allow us to write out perturbative expansions. And we can write out a perturbation theory in powers of an interaction. And here I've drawn a series of diagrams which form subset which includes some ladder diagrams. Okay? And I've attached them to some object called sigma, which I'll describe in a minute. But the basic building blocks of these diagrams are that they include bold Green's function lines. And a bold Green's function line is the interacting Green's function. Okay? And it is a function of the momentum of the electron and the frequency of the electron, or through Fourier transforms, the spatial location and the time variables. Okay? The other building block is a thin line. All of these lines in this diagram are thin lines. They're given the symbol G0. These are non-interacting Green's functions. The wavy lines are Coulomb interactions. And everything I'm going to talk about in my presentation, we reduce a Coulomb interaction to being a local interaction, which when you do a Fourier transform means it's Q independent. And we replace it with just a vertex, and we give it a symbol called U. And that is the Hubbard U. And I'll come back and talk about that more. But the idea of Feynman diagrams is that in order to understand the full perturbation theory, we don't just sum this set of diagrams. We, in fact, have to sum all possible permutations and expansion orders. And they're going to have 1 over factorial terms because there are factorially many of them. They're going to have u to the n given the number of vertices. And they're going to be some complicated function of a number of Green's functions that are non-interacting. Okay? Now, if the interaction is weak, that's a good thing because low-order perturbation theory probably will work in that the higher-order terms become vanishingly small. But if the interaction is strong, the expansion order is large. And again, going back to our definition of strongly correlated, that's one of the possible viewpoints of what it means to be strongly correlated. So if you take nothing else away from the many-body segment that I present here, this would be the thing to take away. And that is what is called the Dyson's equation, which allows you to write the interacting Green's function on the left-hand side as a continual sum in what's a very trivial mathematical formula that can be essentially converted to relate the full Green's function to the non-interacting Green's function and a new object called a self-energy. So you put a particle into the system and you let it propagate. And in essence, all you need to know in order to understand the interacting problem is how is it that if this 10 to the 23 particles are in equilibrium, when you put a new particle in the system, how has it disrupted the system? And how does that have a feedback effect on the particle itself? And for that reason, this object is called a self-energy. By putting it into the system, yeah?
And what's the self-energy in terms of drunk man?
The self-energy in terms of the drunk man. That's a good question. The self-energy in terms of the drunk man. As he goes out to the bar, he interacts with different people, right? And then they convince him to go to different bars, and then he winds up at a different place at the end of the night. Okay? So if there weren't other people, he would go to the bar and he would have his drink and then go home probably because he'd be bored, right? But because there's all these 10 to the 23 other people, interesting things going around, he winds up somewhere else because of the 10 to the 23 particles. That was a great question. I've never been asked that question. I've never even thought about it. So that's great. Love it. OK, so I thought about deriving it, but I got into S-matrix representations and equation of motion approaches for deriving Green's functions. And it turns out it is, at minimum, a couple of solid pages of algebra. So I'm not going to derive them. I'm just going to write them down. The full Green's function is written this way. And it looks like 1 over omega minus epsilon k minus the self-energy. But the non-interacting Green's function is really the simpler object. It just says I'm a simple function, and I have a pole when the frequency is equal to the energy of the problem, okay? Or the energy of the particle. The single particle self-energy is the difference between the interacting and non-interacting system's energies. Now I say energy, but these are complex functions, so it's not really just energy, okay? But you can write that the self-energy is the difference between the inverse non-interacting Green's function minus the inverse Green's function, okay? So
now the definition was cycles, right?
Did I flip them?
So to make this equation to make sense, you need to define somehow independently sigma, right?
I have not. Oh, so right. So what you would typically do is you would explicitly define G0 to be this, and you would solve that using this S-matrix approach or a equation of motion approach. Okay. So G0 is a given. Okay. And then you define the basic building block equation at the top, which looks like G equals G0 plus G0 sigma G0 plus sigma G0 sigma G0 plus dot, dot, dot. Follow? Or is this not the origin of your concern?
Right, I mean, the definition of G is more or less clear, right? It's the same as G0, but with exact eigenfunctions instead of bare non-track eigenfunctions. But the definition of sigma is like it, right?
That's it. So maybe I can help.
Yeah, go for it.
Right? The definition of sigma is in that line on top.
Yeah, so for
is elements, you can think of them as elements that repeat themselves in the Green's function expansion. So you have a particular diagram that appears, maybe you can draw like the Hartree diagram, the improper diagram.
I'm not going to get into that, and the reason is I understand exactly what you're making reference to, which is if you do a formal derivation of Green's functions and non-interacting Green's functions and self-energies from an S-matrix approach, you can clearly see a formal definition of the self-energy, okay? And it would involve this fully interacting Green's function that, like you say, has dressed objects, not just non-interacting ones. It includes these additional time propagation terms, etc.
My question in different ways. Probably many of us know the definition of sigma in terms of this, in terms of the diagrams, right?
Sorry, in terms of what?
In terms of diagrams, is there a simple, straightforward definition of sigma without referring to diagrams? In the same sense that there is a straightforward definition of G without referring to diagrams, right?
Isn't it just live on the screen?
Yeah, it really is. It really is that you have formally decided to define a new object. And if you are okay with G0 and you're okay with G, then you can happily define a new object.
You can also define it in terms of functional derivatives. So you can define a function of
yeah.
have to be diagrammed. Yeah. Then you take the first functional derivative, that's the Green's function, and the second one.
Yeah, so I'll show that. But again, if you're unhappy with the diagrammatic representation, but there is a mathematical representation of your Luttinger-Ward functional. So maybe that's a happier way. But at least in a presentation, you'll see this in all presentations. We're not going to write those things out, so we do diagrams. But it is a very good question, okay? All right. So for the purposes of today and most of the summer school and most of what condensed matter theorists do, any problem of interactions, at least at the single particle level, really boils down to understanding what is the self-energy of the problem. And if you understand the self-energy and you can solve the non-interacting problem, which typically you can do, then you can write down the interacting propagator, and then you can start to make solutions. For example, the density of states is given by some particular integral over that propagator. Same with the energy of the system, etc. So there's a lot of properties. Essentially, most single particle properties can be obtained from that single particle propagator. Now, many-body theory, in the context of what I've just sort of presented, involves Green's functions and self-energies, and that's sufficient for properties like density of states or the spectral function. Those are measured in experimental probes like STM or angle resolved photoemission spectroscopy that essentially directly probes the imaginary part of the Green's function, or A of k and omega. And many times, if you've taken a single course in many-body theory, that's essentially where you would get. So what I've just thrown at you in what, 2 slides could be an entire course, okay? Trying to understand the details of that. There's a lot of many-body theory that happens beyond the single particle level. And these are referred to as 2-particle, 3-particle, 4-particle, etc. objects. And Lichtenstein the other week tried to talk about some of these objects, these complicated vertex objects. So we give different symbols to these things. Here I'm going to use a gamma, primarily a gamma, to represent a vertex function, and a chi to represent a susceptibility. And you've probably encountered susceptibilities even in your undergraduate quantum course, E&M courses, etc. Okay. Now, susceptibilities are really important because most experimental probes, you go and look up the literature, you'll find experiments on optical conductivity, Raman spectroscopy, NMR, neutron scattering. All of those things are not given explicitly by single particle propagation. It is explicitly a scattering problem, and scattering problems involve initial states and final states, and therefore it's a two-particle operation. Okay? These things, it turns out, are also necessary for phase transitions. So I'm going to have to talk about them because the whole point was to try and talk a little bit about phase transitions. There's other objects, for example, screened potentials. If you've ever heard of a GW approximation, you may have encountered that in density functional theory plus GW, et cetera. And when you put all of these things together, you get what are referred to as the Hedin equations, which show you that Dyson's equation is really just a very small part of the relationships between these what are standard many-body objects. And in order to have like a full understanding, you need to be able to understand from the self-energy or Green's functions how to get vertex functions, how to get susceptibilities. This W often is skirted. Often you don't particularly need it because there are direct paths between these guys that sort of get you around it. But you can also obtain this effective screened interaction. Okay? So it really boils down to if only we could compute chi and gamma, etc. Slam. What about vertex? So what is a vertex? You guys have probably seen diagrams that look like this. This looks like what's called a three-point diagram. Lichtenstein talked a little bit about this. You have a boson on one side, and you have a fermion in and a fermion out. So you conserve your lepton numbers if you're into high-energy physics and all that kind of stuff. If you take two of those and you put them end to end, you have a diagram that will look like two electrons go in, they scatter with a phonon or a photon, and two electrons go out. Okay? So this right here is typically what people think of as a vertex in a Feynman diagram. Okay? And a single scattering event, you go to your high energy physics, and the coupling between an electron and, a charge rather, and a photon is given by your fine structure constant, which has some specific value. Okay? So in high energy physics, a vertex is just some number. It's somewhat disinteresting. But in a system of 10 to 23 particles, that vertex might have a lot of structure. And that's because it's some effective vertex that's summed over many different types of contributions and many different interactions. Okay? So the vertices I'm going to talk about are not what's drawn here, not the three-point vertex, but the four-point vertex. And basically, we have energy coming in and energy going out. And when you work out the details, I think I have a couple slides where I try and justify why there's as many parameters as there are. One of the issues computationally is that if I'm writing a computer code and I want to write down what my Green's function is, my Green's function has two variables. Each Green's function has an energy nu and a momentum k. And say, each vertex that's a four-point vertex actually has two fermionic frequencies, a bosonic frequency, two momenta associated with the fermions, and one scattering Q vector associated with the boson. Okay? So we've gone from a two-dimensional object up to a six-dimensional object. So if I was to take some grid, like 10 by 10 grid, and 10 to the 24 points, or sorry, not 10 to the 24, 1024 points in omega, the Green's function is something I can store on my computer. It's like a megabyte. Okay? But you take that same grid size and you store your vertex function, and you're talking about 16 petabytes of information. 16 petabytes of really boring information, it turns out. So this is really the struggle with trying to address these higher order objects, is that the dimensionality of the problem has grown to be a really a bottleneck. Okay? So it was just mentioned that all of this can come from, yeah?
Could I ask something about the previous slide? So I'm not familiar with the electron having a frequency or so. Could you define what mu and k are?
Its frequency in the context that it has an energy. So it has an energy, and I'm going to call that energy a frequency.
Okay, so it's just
H bar, E equals H bar omega. So or H bar nu in this case. Okay?
and k is momentum.
And K is the momentum. Okay? Yeah, great question. So we translate the energy to a frequency, by just saying it's h bar times the frequency. Okay? So the frequency and the energy are interchangeable, and that's represented in your equation for the Green's function right here, where it's got a frequency, and it's got an energy, and they're subtracted, therefore their dimensionality is assumed equivalent, because I dropped the h bars, and everyone else drops the h bars. Okay?
H bar equals 1.
No, everything. There's no such thing as h bar. I'm just joking. Right. So it's just mentioned that all of this can also come from what's referred to as a Luttinger-Ward functional. And it's a certain set of, for me, I'm most familiar with it as a certain set of diagrams, this phi set of diagrams. And we can write out a free energy in terms of Green's functions. And then we have the ability to add a free energy functional. And when we do that, diagrammatically, the self-energy comes out as being a functional derivative of that free energy functional, which is a function of the full interacting Green's function, where we essentially go in and we take a derivative, and that means reduce the order. So that means go in and cut one Green's function line, or remove it, right? So each diagram, you just go in and you remove one Green's function line, and you go from the Luttinger-Ward functional to the self-energy. So I'm going to talk primarily about things which evaluate self-energies, but there are problems in condensed matter physics where it might be beneficial not to directly evaluate self-energies. In fact, most people don't directly evaluate self-energies. They do something else, or they evaluate Luttinger-Ward functionals, because from that functional they can obtain a self-energy. Okay? So there are multiple routes, and there is a stationary, what's referred to as a stationary point, where that equals 0, which returns you Dyson's equation. Okay? Right, so these things are referred to as two-particle irreducible objects. So sometimes we'll use this language, what is the reducibility of a diagram? And that means that it's not possible to break the diagram into all of its pieces by repeatedly cutting two lines, for example, is two-particle irreducible. I wanted to also talk about susceptibilities. In the top left corner, I've written that this is the best paper ever written. It's by a really nice guy named Georg Rohringer, and it was published in 2012, along with some Italians and a bunch of other people. And I say it's the best paper ever written because everything that I know about this content really comes from this paper. Okay? And realistically, it should be a textbook on the subject. Okay? So if anything I say is unclear, you go look at this paper, and it will not be any more clear until you spend weeks and weeks and weeks poring over the notation and understand all the little nitty-gritty details of the Fourier transforms, and et cetera, that give you all this stuff. Okay? So I'm going to show you some of the content from that paper. Sorry. So I just want to orient you in your mind. What are the objects we're talking about? In order to get susceptibilities, we need not just one particle Green's functions, okay, where we put one particle in the system, we let it propagate, but we also need two particle Green's functions. So that means we have 4 possible times. Okay? So we have 2 particles in at tau 0 and tau 1, and 2 particles out at tau 2 and tau 3. So we put 2 particles into the system. They move around, and at some later time, we pull them out. Okay? So there's some insertion of time ordering operators to force causality, because I don't want to deal with a bunch of heaviside functions. But when you write out your 2-particle Green's function, it becomes quite a mess. Okay? We have spin objects for all of them. We have times and or frequencies, but it's much easier to work in times at the start, and momenta rather than spatial coordinates. And we now have a series of 4 operators, which 2 of them are creation and 2 of them are annihilation operators. Okay? So my only point here is that it becomes a more complicated object. You don't need to necessarily focus on this equation, just this conceptual picture of what that object represents. Now, the generalized susceptibility with all of those same indexes as the 2-particle object, okay? You look at the indexes on the 2-particle Green's function, they look exactly the same as the indexes on the susceptibility. And that's because the susceptibility is fundamentally a 2-particle object, has the same number of degrees of freedom. And we just subtract from it certain combinations of single particle objects. This is sometimes referred to as a Wick decomposition. There are, in fact, many basis representations for these susceptibilities. Here I'm writing out from that paper I mentioned the particle hole basis. Okay? And we're free to take one of those times and set it to 0. And that's pretty important to do. Actually, it's not important. When you do the Fourier transforms, it all flattens out anyways. So we can, right from the beginning, set one of the times to 0, and then put the rest in relation to each other. But we also, given a specific diagram that's been drawn, we associate some of the momenta to be momentum conserving. So that says that I have a k in, a k prime in, and a k plus q out. And this probably should be k prime minus q, but there might be some detail hidden in here as to why that's not, OK? I'll think about that. Hidden here is actually some basis definition. And sorry, it's a little bit fuzzy. Is that there's some specific association of frequencies. Probably everything's fine because I have an omega plus nu, and I have a k plus q, and I have omega prime plus nu, and I have a k prime plus q. OK? So that's a big mess. So what remains here is to integrate over the 3 remaining times. OK? And this is just the equation now for the Fourier transform that you want to perform. OK? And those details, the only thing I want to focus on is because there's 3 temporal degrees of freedom, you wind up with 3 frequencies when you're done. OK? So that's the origin of the 3 frequencies I was talking about before. 2 of them are fermionic, and 1 of them is bosonic. Right. So when it comes to things I'll talk about later, I mentioned that there's many basis representations. We often are not interested in particle hole bubbles. Often we're interested in a spin-spin correlation function, or we're interested in a charge-charge type object. And so we can actually write out the same sets of operators that come here, OK, in sets of creation and annihilation operators, which look like a number operator, which is given the symbol n. And we can write out subsets of those, OK, such as the total number of particles at a certain site times the total number of particles at a certain site at time 0. And this is a correlation function as well, or a susceptibility. But you see that this susceptibility, and this is a susceptibility that's much closer to what's observed in an experiment, because it only has 2 times, right? The result of there being a 0 and a tau, not a 0, tau 1, tau 2, tau 3, means that the result only has a bosonic frequency and a scattering Q. OK? It is somehow an inferior object. And it's for that reason that this stuff is referred to as a generalized susceptibility. So that, yeah, in order to get down to this, I would have to take this object, and I would have to integrate over all of its internal degrees of freedom to reduce down to this. I'm going to do one more slide, and then we'll break. And that's basically perfect, because that's the end of my many-body intro. So the last big object, how many of you have heard of the Bethe-Salpeter equation? OK. So the nitty-gritty details of that equation are essentially right here. It's that you have a 2-particle susceptibility, which is referred to as a direct term. It looks just like 2 single-particle Green's functions multiplying each other. OK? So the direct term just looks like this. And then it contains, if you've ever heard the phrase vertex corrections. This was a plague for me when I was a PhD student, because a referee would say, oh, but you didn't include vertex corrections. And what they mean is their favorite set of diagrams which they feel is important for vertex corrections. That's typically the problem. So the reason why this is important is that you can take this equation, which looks like a big mess. You have a lot of double primes, triple primes, et cetera. These are all, they can be seen as matrix objects. So you can take the bosonic element away and consider it to be a matrix in the 2 fermionic frequencies. Okay? So now you have matrix multiplications. So that means that the repeated indices are essentially summed over. So you can take this matrix equation and you can invert it. And in a much simpler notation where we throw all of the degrees of freedom away, we see that our full chi on the left-hand side looks like chi 0 over 1 plus 1 over beta squared, chi 0 times gamma. Okay? This is really important because it can happen. So I mentioned before that the signal of a second-order phase transition is a divergence in chi. Okay? And that has to do with a diverging correlation length. And so in this formula, you would get a divergence when the denominator, okay, or the inversion of the Bethe-Salpeter equation diverges. So that happens when an eigenvalue of the chi0 gamma matrix gives a -1, which it might. And I say eigenvalue because you have to be in some basis where that multiplication of things happens to be diagonal, okay? At the point that any eigenvalue diverges, you must have a phase transition. They don't all have to diverge. Now, which specific phase you have now depends on which Q vector diverges or which susceptibility you're even looking at, okay? And it's really hard to search for phase transitions using susceptibilities in a theoretical context because you don't know if some other susceptibility might have diverged earlier or at a higher temperature. So that actually ends the many-body section. So I guess we can take a short break. My goal was to start here and then ramp things up. And I can see from your faces by the end of the last little lecture some deer in headlights sort of looks because it gets pretty technical with too many little variables. So what I'm going to present now has the intention of bringing it back down to problems that I think most of you will have solved. Some of them I think like explicitly. And then something that I think is just really cool that I've been working on recently to help you solve the same problems that are much more complicated, okay? And this will all be clear as I get into it. So what I'm going to talk about is, I think, something fun. I'm going to start with some philosophical questions. I'm going to talk about evaluating Feynman diagrams. I'm going to explicitly talk about Matsubara sums. I'm going to explicitly define what Matsubara frequencies are for anyone who has never seen them, et cetera. And then I'm going to talk about some of the numerical challenges that come just from trying to sum these objects, okay? And then I'm going to introduce this computational method when my student coined the phrase algorithmic Matsubara integration. It's really cool stuff. So I said I was going to start with some philosophical ideas. This is my buddy Phil. He works at Scotiabank in Toronto. And he basically gave me some of these ideas because he's a very brilliant banker. And we were just having a discussion about what is the fastest way to solve a problem, okay? And we were talking about computers. You can have classical computers or quantum computers. Basically, a computer is a system designed to solve a specific problem, or it's a collection of problems that allow you to accomplish some greater task, right? And in condensed matter systems, you'll see all kinds of papers about cold atomic gases where they create quantum simulators. They say, don't solve the Hubbard model, or don't solve an Ising model or a Heisenberg model. Just create a system that obeys the same Hamiltonian and watch it. And that's what you call a quantum simulator, okay? It just mimics the Hamiltonian, and you can just probe it directly. So that's kind of like a computer that exactly solves the problem you were setting out to solve to begin with. More recently, you'll hear people talk about machine learning. Machine learning is a really good tool to use if you really don't know what your data is in a high-dimensional space, or you don't know how your data is even related to each other. Now, there are people trying to use machine learning in physics, and I hope with great success. But on a fundamental level in physics, we understand a lot about what's going on in our system, okay? And I'm gonna talk about this. Another tool that's very common is Monte Carlo, where we have a known probability distribution, and it's just of such a high-dimensional space that it's very hard to understand or to evaluate, okay? So Monte Carlo is really great for low accuracy problems because it's very easy to get 10 to the minus 3 accuracy because the error goes as 1 over the square root of the number of samples. But it becomes very hard to get extremely high accuracy results out of Monte Carlo, okay? So talking to my friend Phil, he said, the fastest way to solve a problem is for someone to just tell you the answer. And then he burst out laughing. I thought it was really great. And then we talked about this a little bit more. And what we decided upon is that, and I don't know if this is true. I don't know if this is formally true. Someone who's better at math can tell me if this is wrong. Is that if you can generate a closed form analytic solution, then it stands to reason that this is the faster solution, just evaluating that equation, than any other method. I don't know formally if that is correct, okay? But I'm just operating with that mentality. As if if I just give you the answer, it's just written down. You just have to plug the numbers in. That should be the fastest way to solve the problem.
Yeah, so this depends on your definition of fast, analytic, and closed form.
Agreed. So the problem that we want to solve is interactions in a system. And one method is doing infinitely high order perturbation theory, okay, via Feynman diagrams. And this has a name. It's called diagrammatic Monte Carlo. And in condensed matter physics, it's met some level of success. And Guy will talk about doing diagrammatic Monte Carlo on totally different systems than what I'm talking about, okay? But the basic structure of a Feynman graph is that you have a series of external legs, and those can be non-interacting Green's functions. And then inside, you have a bunch of internal lines that are also Green's functions. And they have a series of momenta that have to be summed over, because those are internal degrees of freedom. So the Feynman diagram has to be summed over all of its internal momenta and internal frequencies. And in there as well, you have vertices, which occur when the lines meet. And for us, for Hubbard-like models, that's just a constant value u. So mostly for a given diagram, you don't care. You just count up the number of vertices. It comes out of the sum. You have a u to the n sitting there, okay? But the result must actually be integrated over all the internal variables. So the problem we need to solve in order to understand interactions is just some series of known integrals, okay? So say we want to compute the integral over the frequency of a Green's function, just one Green's function that happens to be sitting inside this equation. We know that there's a pole in the non-interacting Green's function because it looks like 1 over omega minus epsilon k. It's also not a very friendly function to integrate because it's somewhat, it's a 1 over x integral, okay? Now, in this case, we can't really remove the pole, but we have standard tools of contour integration where we would simply replace the frequency with a complex object plus a small imaginary part shift, right? And then we do an integral along the real frequency axis and around a contour, either in the upper half plane or in the lower half plane. Here I've flipped the direction of the integration, okay? And then we use what's called residue theorem. We just count the number of poles inside, and that gives us factors of 2 pi times the number of poles, the residues of those poles. How many of you have used residue theorems? Good. So everyone understands you could do this integral. Everything is all fine and dandy. What if you want to compute integrals of Fermi functions times Green's functions? Hypothetically. The problem is that a Fermi function, which looks like this, will have a pole if you extend the energy to the complex plane, and it'll have a pole when that exponential gives a -1. So in a complex unit circle, that'll occur for factors of pi, okay? And so this is the definition of Matsubara frequencies, which is if you have a fermionic system, you get a series of poles of the Fermi functions that have a specific form of 2n plus 1 times I pi over beta. And if it's a bosonic distribution function, not a fermionic one, okay, then you'll get an even function. So for fermions, what this means is you now have you don't just have the pole from the Green's function. You have an infinite series of other poles. And those poles are your Matsubara frequencies, okay? But in general, you just use the residue theorem. You have an infinite sum of poles. You just have many more poles, and you have to worry about this infinite sum. But ultimately, what this lets you do is it lets you rewrite your integral with Fermi functions into an integral of Green's functions. Here I've dropped the G0 notation. I apologize. As just a sum over the Matsubara frequencies. So the sum over the real frequencies is equivalent to the sum over the Matsubara frequencies where all the Fermi functions have been dropped. Okay? And then we can equate the sum over the poles of the Fermi functions of the Green's functions to the sum over the residues of the Green's function times the Fermi function. Typically, what is done is just up to this step. So when we translate a Feynman diagram in Matsubara space, so what is done is just up to this step here. Okay? When we translate a Feynman diagram, we immediately presume that there's no Fermi functions in there, and that our Green's functions are all Matsubara frequency objects. And then we have to perform this sum by just evaluating that integral. Okay? However, it turns out, yeah?
May I ask, why is it that all the poles are on this complex axis?
Sorry, wasn't what?
Why do you know that all the poles are on this axis, basically on the imaginary axis?
There's some details as to how one obtains these equations. What you do is you essentially solve your integral twice, okay? And then you take the limit of this contour going to infinity, and you can find the equality between the initial integral you're trying to solve and this equation, okay? Which happens to only care about the poles along this axis. But just as well, you would find that it was equal to the sum of a different equation that includes the Fermi function, but evaluated at the poles of this function, okay? So I bring this one to this side. Those are all the poles of the Fermi functions, plus the poles of the Green's function, equal to 0, okay?
I was wondering, why does I think you claimed that the Fermi function has poles where you have the red dots.
Yes. That is because the Fermi function is given by this equation, and that looks like e to the 1 over e to the beta z plus 1. So when your denominator is equal to 0, that's when your denominator is equal to minus 1. So you have a complex phase, right, which has a minus 1 e to the I theta, okay? Z is a complex number. It can have a complex component. So say Z is equal to x plus I theta. Don't worry about the x component. Just for now, just think that it's completely imaginary, okay? Which those poles are completely imaginary, okay? So if they are completely imaginary, then when is e to the I theta equal to minus 1? That occurs for pi, 3 pi, dot, 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 up to infinity, okay? So they're always separated by factors of 2 pi. And it happens that because there's a beta in here, you get factors of 2 pi over beta times n and their complex number, okay? With a 1 shift because it's a fermion and no shift if it's not, okay? This is why I think it's relevant to do this. Not literally everyone has seen it. Okay. I only have 30 minutes and I have 25 slides. So we're going to go quick. All right. Matsubara frequencies are problematic for numerical data. There's a relationship between a Green's function in real frequency and a Green's function in Matsubara space. And unfortunately, if you have the Green's function in real space, it's very straightforward to obtain the object in Matsubara space. This is what's called a Wick rotation, but it's also given by this equation here, which is essentially just you find that complex pole, and you'll pull out the correct Green's function. But the direct inversion of that is actually problematic because a small fluctuation of the Green's function on Matsubara axis could result in a large fluctuation on the real axis, okay? So if you have numerical data that's generated in some sort of Monte Carlo process and you have error bars, that means there's now an infinite number of solutions to the real frequency Green's function, okay, that would give you back the Green's function on the Matsubara axis when you perform this back continuation, okay? So this is a big problem for non-thermodynamic properties where you don't also integrate over the frequencies, where you actually want a dynamic problem, okay? But it's a problem for something as simple as the density of states. So this is, for example, a 2D square lattice type binding density of states, and it should have a very specific shape, and we get all of these ripples when in fact we should get something that looks much smoother, okay? So there's a ton of numerical work that goes into evaluating these many-body objects in the Matsubara axis, but the process of obtaining them in real frequencies is an ill-posed problem. Now, there are many numerical tools that exist. For example, there's if your data is highly accurate, you can use this method of what's called Pade approximates. I'm missing a little accent there. There's also maximum entropy inversion. I'll advertise that we have a code that's quite straightforward to use. If you ever have to solve a problem like this, just go look this up. It's just called maxent. And there's also other methods which are coming around that are just trying to give you a better representation of the real frequency axis problem, because we live in the real frequency world. there's a bigger problem, and it has to do with how the problem compacts with decreasing temperature. So as you decrease the temperature, beta in this formula increases. So the spacing, I erased it, the spacing between two Matsubara frequencies shrinks. As t goes to 0, the spacing between them is 0. That's a huge problem, OK? And just to try and illustrate that, say I have a function that I want to integrate. And there's no physics in that function, so that as I go down in temperature, it doesn't even change. And if I want to perform an integral as a discrete sum, and I integrate the first 20 frequencies, if I go down in temperature by a factor of 2, then those same 20 frequencies only give me half the domain. Okay? And so as t goes to 0, if I start at 0 frequency, or at the first Matsubara frequency, if I want to just get to the hump in that function, it would take an infinite number of additional frequencies to get you there. So there is no Monte Carlo process that I'm aware of that allows you to directly overcome that issue. Okay? That's a really big issue. It's a big problem. So it is not just that we can't get the frequency object. It's that as beta gets large, we can't even obtain the Matsubara axis object. Okay? So it's like a double whammy. So types of problems you might want to solve. A polarization bubble. How many of you have seen the evaluation of a polarization bubble? This is something you can look up on Wikipedia. So you don't have to take my word for it. But it's a simple application of residue theorem. It involves two Green's functions, one with a frequency omega. There's an external bosonic frequency that gets picked up on the second Green's function. So this is it in its formality. And you see right away that the first Green's function has a pole when z1 is equal to epsilon k. The second Green's function when it's equal to epsilon k plus q, because it's at a different momenta. Plus, there's now a bosonic frequency hanging around. Okay? So we know how to solve this using residue theorem. We simply evaluate our equation for residues. We evaluate the first residue. We get a Fermi function that comes out. Okay? We evaluate our second residue. We get a Fermi function that comes out. The result is just the sum of those. And it gives this very standard formula, which is a Linhart dielectric function. Okay? So this is a standard exercise in a many-body theory course. So go through it if you're interested. What's interesting about this is you've analytically solved, depending on the dimensionality of the problem, 1 over d plus 1 fraction. So if you're in a 2D system, you've solved 1/3 of the integrals analytically. Okay? It's also really powerful because it's valid for any single band dispersion for any material, any lattice without a basis, okay, in any dimension at any temperature. It's a very broadly applicable equation. Okay? And there is a tool. The whole reason these Matsubara equations exist is because on pen and paper, the process of going from imaginary frequencies to real frequencies is trivial. It's referred to as analytic continuation. And all you do is you replace the bosonic Matsubara frequency here with a real bosonic frequency plus I times 0 plus, or a very small effective parameter that might describe some impurity scattering in your system. It is a trivial problem now to evaluate that for real frequencies. Okay? So you can look at some low-order diagram. And people have done this. And you can go through the process of writing out a second-order self-energy, which might look like this with a particular set of labels. Okay? And what we see is that 2 internal lines are independent variables, and the third is completely dependent upon the others. So now we have 2 Matsubara integrals to perform, right? We have a sum over the first frequency and the second. I've dropped the notation that we still have 2 momenta that have to be summed over. And each of those has d elements for a d-dimensional problem, like a kx, a ky, kz. Okay? And you can just go look this up, and you'll get an equation that looks like that. So instead of 2 terms, it happens to have 4 terms. Okay? In that there are 4, you multiply the numerators out, you'll get 4 multiplications of Fermi and or now bosonic functions. Okay? And when you've done this, again, you have solved 1 over d plus 1 fraction of the integrals analytically. It's valid for any single band dispersion in any dimensionality in any temperature. And you can directly analytically continue it to get the real frequency result. Now you still have to, even once you've done that, you still have to integrate all the other k integrals. Okay? And for Hubbard-like models, the bare vertex just gives u to the n times the number of vertices, which in this case was just a 2. Okay? So does everyone follow at least the logic here? So is there any reason why I can't take any arbitrary diagram and do this? So I find some complicated diagram. I look up this paper by Riccardo Rossi, who's at this CCQ now in New York, very fancy place. And they have this paper on the archive. And somewhere in there, they draw this ugly diagram. And it has 17 Green's functions. And it has 9 independent variables and 1 external frequency. So you would have 18 momentum to sum in a 2-dimensional problem, for example. And you'd have 9 nested frequency integrals to perform. So there's 27 nested integrals. Right. But conceptually, we know exactly how to do this. We have a complete knowledge of the pole structure. We just sequentially start to perform these integrals. So the idea would be at the end, you would have a term that looks like u to the 9 times some summation over all of the internal k vectors times some really complicated, maybe, equation that is a function of all of those variables. And when you've done that, you've again solved it in 1 over d plus 1 fraction of the integrals. It's valid for any single band dispersion in any dimensionality. And you can trivially analytically continue it. There's a more subtle point, which is you can evaluate it to machine precision. So when I say exact, I mean arbitrarily exact to whatever your computer's machine precision is. So the question to you guys, how long do you think it would take you to do that? Earlier last week, you were given a homework assignment by Dmitry Abenin. So would you guys like this as a homework assignment? You all know exactly how to do it. So it's a perfectly tractable problem, right? So why not? If I was teaching a course, I could just assign it and say, on your next assignment, please hand in the solution. And so a more general question is, why are there not just lookup tables quoting analytic formulas for arbitrary Feynman graphs? Why do those not exist? Can someone answer that? Someone must know. Yeah.
Because the idea of a Feynman graph is not to write analytical formulas because they're huge.
Because they're huge.
So it makes no sense to go step back.
It actually makes a lot of sense because I really want to evaluate it. Okay? And again, going back to my statement at the beginning, is if I just had the analytic formula, if someone just wrote it down and put it somewhere, then it would purely be an issue of me evaluating it.
When you want to evaluate, you can reproduce it by the Feynman diagram. So it must be.
OK, so here's this complicated diagram. Okay. So go ahead.
So it's like a technical question. So it's not something. It's just writing down with patience.
Writing it down with patience. Yeah. So I like to think that I'm mean to my students, but I'm not that mean. So this particular diagram results in 337,982 terms. So then the more broad question is, how do I know how many terms there are? How do I know that? Well, this is a very conceptually straightforward problem, right? We have all these computers. We can just write a code to do it, OK? I don't know if I'll quite get to the end of this in this lecture time. So if I don't, I'll either just skip to the end and give you sort of a punchline. If you're interested in this, there's a paper in the archive just from like a week or two ago with my very happy-looking PhD student and one of the other faculty members at Memorial University. And the whole project was just to attempt to write a computational algorithm to construct the analytic solution to frequency integrals of an arbitrary Feynman diagram. So not that far from what you're saying, where you maybe don't really want to store the full analytic solution, but given a diagram, can you just construct the answer? Okay? And it turns out that, I mean, to give the punchline, is that diagrams of arbitrarily high order can be constructed in just a few seconds. And then you have the analytic formula, okay? Of lower order, thousands upon thousands of times per second. And once constructed, never have to be reconstructed, just evaluated. Okay, so it's a huge computational advantage. Now the name of it, which is called Algorithmic Matsubara Integration, the idea came from something called algorithmic or automatic differentiation. How many of you have heard of that? I'm blown, yeah, you have, because computer science people know this stuff. It is a trivial point in computer science that given a function, so the way, just so you know, Kuhn, in physics, if I write a computer code and it's f of x, and then I want a derivative of that, I take f of x plus h minus f of x, I divide it by h, and I call it my derivative function. And that's how I do it. That's how most people numerically in physics do it, even when they have complete knowledge of the function. And it turns out that automatic differentiation is a tool set that allows you to essentially construct the analytic representation of arbitrarily high-order derivatives in a symbolic manner. And then they just get evaluated. So the evaluation of a derivative takes just as long as evaluating the function, and can be done side by side. Okay? So the name is essentially stolen from there. In that case, it's a repeated application of chain rules. Just the idea that you can do high-order derivatives by just taking one derivative and then another, and then another, and then another. Okay? And if you're interested in that, you can check out Python implementations like AlgoPy. It works super fast, and again, it's like the same amount of time on a computer to just evaluate the functions. OK. So this is actually quite a departure from what is typically done in Monte Carlo using Green's functions. And the reason is that typically in standard diagrammatic Monte Carlo, each Green's function gets assigned a frequency and a momenta. Okay? And then you force that at each vertex you have energy and momentum conservation. And then they maintain that by using what's called a worm algorithm. And Lichtenstein talked a little bit about that later. Guy's going to talk probably at some point about an inchworm algorithm. It's a totally different thing. Don't get confused. Right. So in order to implement such a problem that's just a symbolic representation of all these integrals, we need to update each Green's function for each frequency and energy. But in order to do this, is that we should rewrite each Green's function as a linear combination of all possible independent frequencies and independent momenta. Okay? So that means that here's some explicit example where I have -4 as an energy, and I have a new 1. I have 1, and I have a new 2, and I have a -1 and a set of frequencies. Is that the first Green's function has a epsilon of 4, but it has a 1 times I nu 1, a 0 times I nu 2, and a 0 times I nu 3. Okay? It's just a linear combination of I nu 1, I nu 2, and I nu 3. And we do that for all of them. Okay? So I skipped the previous slide, but because I realized that this should have been written immediately after. So that same equation gets written now explicitly this way, in some stored format of just some simple integers and maybe a double number. Or you can actually replace this also with a symbolic representation of the epsilons. Okay? So the details, again, are you take a Green's function, and it's no longer a frequency minus an energy. It's an array of possible frequencies, or a linear combination, and again, a linear combination of possible energies. And by associating a set of momentum-conserving labels right from the start, we always have momentum conservation. We never have to worry about that. And this is exactly what you do when you look at a diagram. You analyze it, and you write all of your labels so that it's momentum conserving right from the start. Okay? So that's a little bit of an extra cost that diagrammatic Monte Carlo does not have to do. It works out a little bit nicer. So the point is that we store that Green's function as something that looks like an energy, and then a linear combination, all of the coefficients of those frequencies. And it turns out those coefficients are never numbers other than 0, 1, and -1. They never turn into 2s. They never turn into 3s. There's never at any stage that should happen. So it's a very simple process as we're going to proceed, that we're just going to add and subtract 1s, 0s, and -1s. OK, so symbolically, these two equations are the same now, because we can look at this set of numbers, and I can construct that equation. So can we write down how to apply a residue theorem on such a such a case. So we have some function that we want to apply residue theorem, so some Fermi functions come out, okay? And we can write down a set of poles. So the first, apparently I got distracted. No, I didn't. So we say, here I have two integrals, and I'm going to do the integral over nu1. The first element has a known pole at 4, and the third element has a known pole at -1 plus I nu2, etc. So the storage or the symbolic representation of the poles looks exactly like the symbolic representation of the Green's functions. So if I want to sub a pole into a Green's functions, I just add the two objects. Okay? So this is some formal stuff that I don't really expect any of you guys to follow, but that's OK. The number of poles is just going to be the sum of a certain number of those coefficients that's non-zero. Okay? And the result looks like some big mess. And I want to just look at this mess. So this is after one integration over I nu p, where p is one of those frequencies. And I want to focus on this, is that this ugly-looking equation has some signs here, a beta, which we don't care about because it actually cancels a beta that already existed. I have a Fermi function that gets evaluated at a pole. And then I have a multiplication of Green's functions. And that multiplication of Green's functions looks exactly like the initial problem. It just looked like a multiplication of a series of Green's functions. But there are now one fewer Green's functions here. So each term in this is in essence a subset of the original problem we set out to solve. So it turns out that this is actually a sufficient solution to the problem. And if you were so inclined, I think any of you who are computationally oriented could actually code this in Python within a couple of hours if you understand residue theorems, et cetera. Okay? On a simple example. It's really not that challenging, just from the slides, the content that I've shown. However, it is sufficient to just repeatedly nest these arguments, or repeatedly nest function calls. But unless you're clever about how you write that, you might actually lose information. So there's actually a little bit of a more elegant way to go about this. And the point is that if we have these three parts that we need, the signs that sit in front that are 0, -1, or 1, and we have the set of poles, and we have the sets of Green's functions, then if we just store all of those objects, then we can reconstruct the answer at the end. Okay? So we can just store those as some set of objects. Once we've done that, very similar to algorithmic differentiation, is you now need a set of new operations that let you reconstruct that. Okay? So I'm not going to get into the details of what these operators are. But basically, we have the multiplications of some signs and Fermi functions to pair the correct signs with the correct Fermi functions. Then we know how to pair the Fermi functions from one integration to the Fermi functions of another integration. That's this cross symbol. And then when all is said and done, we multiply it by the final result. Okay? So I just want to give an explicit example. So the application on this self-energy, which has an analytic formula here, on that example where we put in some specific numbers, if you were to run this through this procedure, you should get this set of numbers. A set of signs, a set of poles, and a set of final coefficients, Green's functions, where none of them have anything except the last frequency. Because the last frequency is the external frequency. And so from this set of equations, we can construct the analytic result, which if you were to check numbers and whatnot, you'd be able to see was equivalent to here. Okay? Given the time constraints, I'm going to skip because all I do at this stage is go through more and more complex problems. Okay? And you can see that even for low-order diagrams, you can get many, many terms. And I am a mean supervisor. I made my student explicitly write out. The hardest one he had to do was a fourth-order diagram, and he had to write out all 82 terms by hand, and so that he could check that all the details of his algorithm worked correctly. Okay? So we did not go beyond that. But it's from that we are able to hypothesize that so long as we haven't made any errors, that weird ninth-order diagram has hundreds of thousands of poles. So I want to get to some point, because I can see I'm losing you guys on details. The point is we have a phase diagram that we want to try and solve. And we have certain diagrams that we want to try and evaluate. It is the case that all quantum Monte Carlo struggle with low temperatures in frequency integration. There are some methods that manage to skirt the problem in some way, or they really hammer it. Typically, every point in this phase diagram, u, t, and mu, has to be evaluated separately. Okay? Every time you change the temperature or you change the u value, it has to be evaluated separately. Now, there are some smart ones that directly sum the self-energy. So u is for free, etc. But with this procedure, you can, for a single diagram, evaluate the whole phase diagram of that diagram, diagrams of diagrams of diagrams, in one shot. Okay? So we can evaluate it for any interaction we want. Temperature is a free variable. We can evaluate it at any temperature. We can evaluate it at t equals 0. Okay? Mu, chemical potential, is also free, since it's just a parameter inside the dispersion. And then you have something that's valid also for any choice of dispersion, whether or not it's an any dimensionality, whether or not it's a two-dimensional system or a three-dimensional system. There is one caveat. Way back when I wrote these polarization bubbles, there's a special case when q equals 0. When q equals 0 and omega equals 0 in a polarization bubble, this equation, the equation I wrote somewhere, I should have put it here, would actually be divergent. Okay? And that's a problem. And the reason for that is that your residue theorem, when q equals 0 and the external frequency is 0, has two poles with it has two poles that are the same. So you have one pole with multiplicity 2, which is totally different. Okay? Your original equation is still exactly correct. Okay? It is still the correct representation. But what you have is two divergent terms that have to sum to 0. And if you look at them in the wrong way, they look to be divergent. But if you extract them, it's a removable divergence. Okay? When you do this on a practical system, you'll actually find pairs of divergent terms that unfortunately are not 0, but highly not 0. Okay? Like actually important contributions. Okay? So all of the divergences are removable, but it's non-trivial if you look at 300,000 divergent terms to figure out how to pair them back up to make non-divergent objects. So the way to get around that is employing residue theorem of higher order multiplicities, which explicitly now uses algorithmic differentiation. Okay? The problem is, and this is where it would have been really mean to a student to assign this, is that when you treat it for multiple poles, if your student was picking out all these special cases where there are multiple poles for this 9th order diagram, is that the number of poles by the time you hit the 9th order diagram is in the billions. Okay? So there is some limit to this, beyond which the true number of terms required becomes somehow uncontrollable. The scaling of what's precisely? The scaling of evaluation and construction is directly linear with the number of terms. Okay?
Okay, what's the number of terms with the order? Exponential? Or factorial or something? Factorial. It
would be less than factorial, but a weird combination. Like, say you have a 9th order diagram.
More than exponential.
It's more than exponential, yes. So just as a summary, which I'm finishing basically on time, this method of diagrammatic Monte Carlo, okay, needs to sum all diagram topologies and internal parameters. And using algorithmic Matsubara integration, we can actually trivialize some fraction, some pretty large fraction, a third or a quarter or something like that, of the problem, and completely skirt all of these issues with complex frequencies. Okay? And the idea is to replace a sum over frequencies and k and topology with just topology and k, where we put in this result from this algorithmic Matsubara integration. Now, there are potentially huge computational savings for diagrams below about 8th order. Okay? And that is actually already about on the cutting edge of what is done in direct diagrammatic Monte Carlo. and we could probably do real frequency applications. So that's where this work would be going. Okay? So we're actually quite happy with that. And again, conceptually, the goal would be to literally just store these solutions for arbitrary Feynman graphs somewhere so they can literally just be looked up. So conceptually, once they're stored, they never have to be looked up unless you hit one of these special poles. And then it has to be reevaluated. Okay? So that's sort of the mindset that we have.